Okay, we're recording. More people coming in. It's our spring break. It's probably spring break for at least some of you out there. And most likely for the ones who it is, you're not here because you're off actually having a break. So it's my break. It should be the quiet time, chance to catch up. But this is like my craziest week of the semester. I'm taking group of students, I think 7 students, to Perry for a hackathon, a workathon. I normally take them to Green Bank, maybe one or two times a year, either spring break, fall break, or winter break. And of course, I take students during the summer for my summer program as well. So I go to Green Bank a lot. And we were going to go to Green Bank because we like setting up, and for those who have been there, we like setting up in the Drake Lounge. That's my favorite place on the whole planet is the Drake Lounge at Green Bank. And we set up a little network, and we're all around the central table, and we just work. They all work on their projects, and it's great because you get like a month's amount of work out of each of them in one week because they're there. There's nothing else to do. There's no cell phone communication. And when they run into problems, they're there with everyone else. They can just ask and they help each other. And so they accomplish a tremendous amount of work in a short period of time. It's really gratifying. But I emailed Green Bank and they said they're full and they have some other programs. So I decided to try Perry. I haven't been there for 2 decades. That's where we started. We prototyped the prompt telescopes at Perry. It's the for those who don't know what it is, it's a radio observatory in the western mountains of North Carolina, near Brevard. It used to be if I remember correctly, a CIA spy center or monitoring center. And for a while, it was a NASA relay center during the moonshots, communication for the moonshots.
NSA. It was an NSA facility.
Yeah, NSA.
NSA, not yeah, NSA, not CIA, right? And then Don Klein, who some of you know, at least if you're in this part, like North Carolina, um, he purchased it some time ago, 25, 30 years ago. I think it was like a land swap where he paid $1 and swapped some land. And it has it had 4 um, satellite dishes, which he's turned into radio telescopes, 226 meters that I think are dormant at the moment, a 12 meter that we've been trying to refurbish as part of the DoD grant and will be going on Skynet, and their 4.5 meter Smiley telescope, which will also be going on Skynet. So I've been meaning to get out there anyway. It'd be good to see the people we're working with. And yeah, anyway, I've been trying to get that ready. I have a proposal due in about a week. I have an advisory board meeting for Skynet. So I'm just like burning the candle at both ends. So I apologize if I'm a little scatterbrained. Um,
FYI,
yeah, go ahead.
I don't think anybody here will break the code, but we're actually going to nominate Don for the Klumpke Award for the ASP, Klumpke Roberts Award for the ASP.
Oh, that's wonderful. Yeah, that's wonderful. He's put decades into good community service of astronomy and radio astronomy,
Yeah.
particularly in North Carolina.
Yeah, I saw the email last week. They open up nominations. I was like, wow, that sounds just like Don. He doesn't know it, but but it just so happens we have him coming in and do a presentation in a couple of weeks at the club, and so he's gonna hopefully we'll let him know there. So
Surprise him. Oh, that's good. Let's see what else. Well, you all uh, nominated me for the Emmons last year, and I got it, ASP award. Yeah, and uh, they asked me to write an article, and for their Astro Beats, and that comes out today, I think. And so I'll send it around. I wrote it, and then got back to me and said, this is 6 times longer than the typical length, 3 times longer than the longest thing we've ever written. Or
Know you were being nominated for that?
what's that?
Did you know in advance you were being
No, no,
nominated?
you all surprised me. It was some subset of you did it, and I appreciate it. And I went out for the ceremony last November, and it was cool. It was deja vu. I had gotten the Trumpler when I was very young, so I've been through it before over there. Anyway, that article will come out today. I'll send it around, and I'm pretty happy with it. I told kind of the entire story of Skynet, going all the way back to my first visit to Green Bank as a high school student, and I have some good stories in there and reflections, culminating in the stuff that we're doing now. What other announcements do I have? Going to Perry, writing proposal. Oh yeah, I mentioned the advisory board meeting. That's next Monday, so I have to cancel our meeting next Monday to meet with the advisory board for Opus and MWU for the two big grants that we've been writing off of. We've been trying to schedule it for months. So there was the only day that worked for all parties. So I'll put it in the email when I send around the article, I guess, but no meeting next week. So, all right. Before we get into module 2, does anyone have anything to share? Questions, comments? All right. Well, I have something to share. Module 3. So let me share my screen. Okay. And we'll get to this, I guess, the next time we meet, because we've done module 2. We start with module 1A, the moon, 1D, the planets, both optical. Then we started 1B, 1C, which is radio moon, radio Jupiter. They're very similar, so we did them together, but we never finished. I forgot that we never finished, and we moved on to module 2. We did that in 2 weeks. Today we're going to finish module 1B, 1C, and then move on to module 3, which is kind of the first serious astrophotography project. Module 1 is kind of introductory astrophotography. Module 2 is intermediate. So module 3, it starts to get serious. And my students have been doing this, and I always do one as well. So I decided to try out the APUS telescope. It's a new telescope on Skynet. It's in West Virginia, in Charlestown, northern part of West Virginia. It's a 24-inch American Public University system. And they put it on Skynet. There's still some dome issues, so the dome breaks like once or twice a night, and we won't have time to go up and help them install a different dome system for a while. But they've been pretty vigilant in fixing errors when they break. This is Ed Albin. And so I decided to test it out, and I'm pretty pleased. And I'll show you how we do this in module 3. Module 3 is pretty expansive. You learn advanced astrophotography techniques. We integrate infrared. We do a Strömgren sphere calculation. Anyway, the students all selected their targets. There's a list, and we do Kahoot questions in most classes. And those who get the most points on the Kahoots, which they get by doing the reading. So this is the incentive. I assign reading. They do it. They get Kahoot points, and whoever gets the most Kahoot points, they get to cash in for first dibs on targets. I don't let the targets be done more than, well, in my class, I have so many groups there. They can be selected twice, I guess, but I'm not going to let everyone do the same target. And anyway, they all selected their targets. They put in a test observation. They come back, they rescale their exposures, exposure durations. They pick which narrowband filters they want to burn a lot of telescope time on. And then they put in a main observation. And so here's my main observation of Monkey Head Nebula. And this is not just a red, green, blue, but LRGB plus narrowband. So where they learn how to use a luminance filter, and they learn how to incorporate narrowband. And it's more advanced techniques you correct for, like we did with the star clusters, you correct for dust along the line of sight, which can be significant for these star-forming regions. And I'm pretty pleased with how this came out. This for a new telescope. As a large field, it's 31, 32 arc minutes. I didn't even have a flat for H alpha yet. So this pink here, which is H alpha, is it's not even flattened, and it turned out pretty good. A little bit of O3, a little bit of color there, and then the LRGB, nice star colors. And I kind of worked ahead and incorporated the archival infrared. I think I have that here. And so here, the infrared, it's two bands from the Weiss satellite. I get to check to see if there's Spitzer data. Spitzer hits kind of popular targets. There may be Spitzer data here, which would be higher quality. But Weiss surveyed the whole sky, so it's like an easy go-to. I know there's going to be data. And this is 12 and 22 microns. And so at these wavelengths, you're getting warm dust, like 300 and 100 Kelvin. So, what's going on here is you have hot stars and the O star, like that one right there. There are O stars and B stars in here, ionizing the gas. So you have star heated gas and it's glowing in optical narrowband like H alpha O3, a little bit of S2. And creating this ionized bubble in H2 region, a Stromgren sphere. And this is pushing up against the gas around it. And that gas, well, inside the nebula, since H alpha is emitting, I know the temperature. It's got to be like 5 to 10,000 degrees to get H alpha to emit. And to get O3 to emit, it's something like 15 to 40,000, something like that. So, I have some idea of the temperatures on the inside. I also have some idea of the temperatures on the outside because of the infrared emission. So not only do they get kind of this awesome picture, and everyone has a different target, so everyone gets a different awesome picture. They frame them themselves, and you can start to tell a physical story. You can do a calculation. You can do, you can estimate how many ionizing photons are being pumped out by the bright stars, which you can kind of count in your image. Temperature information on the boundary. You do pressure balance. This is all stuff we figured out. Those of you who helped to develop this. I haven't yet done the calculation, but I'll be able to get a density from this. And then what the students do to follow up is they, once they get that density and temperature on the inside, they say, oh, there should be Bremsstrahlung radio emission. And they go make a radio picture. And indeed, it's glowing in the radio. So it's a pretty cool activity, Matt. Matt, are you here? Let me spread you all. Yeah,
Yep.
Matt spearheaded this. So anyway, here's another one, Matt, that's in progress.
That outline of the infrared on the H alpha there, that's fantastic.
Yeah, I normally have the I use the heat map and the cool map. I flipped them in this case because it looked better. But you get a little bit of that blue haze surrounding it up here too. You can really see. Yeah, it's really cool. Anyway, I've spent enough time on that. We should get to today's primary activity, which is finishing 1B1C. I don't think it'd take too long. Last time, 3 weeks ago when we started this, we took it slow because a lot of people are not familiar with radio. It's one of the things that we're trying to address with Skynet and this curriculum. It's kind of it's a cycle, right? Most, so I'm abstracting a little bit here. I'm on a tangent already. Most universities have a campus telescope, an optical telescope, but they don't have a radio telescope because radio telescopes are very expensive. They're big, like the one at Green Bank is 6 stories tall, 150 tons, requires maintenance crews to work on it all the time. So they can't afford that. Most universities don't have a radio telescope. A few have a small one, but none have like a 20 meter, which is considered a small radio telescope. And because of that, students, and also the ones that do, they're expensive. So they're not run by universities, they're run by governments. And they're very remote because civilization makes radio noise. So you got to keep them far from everybody. Because of that, students don't really get any experience with radio, even though they should. It's the other regime that makes it to the ground. Everything else, you have to be in space. And yeah, we can't really provide that to students yet. But this stuff makes it to the ground. So it's sad that they don't get the experience, but it's remote, so and it's expensive, so they don't. And then those students grow up and become educators, such as yourself, but you don't have great familiarity with radio because you didn't have it as a student. And into this kind of reinforcing cycle. But Skynet is the solution. The fact that these are remote doesn't matter. We do everything remote through Skynet. And being expensive isn't a problem anymore either because I'm trading. We're building this new amazing control system and scheduling system, and I'm making deals with radio telescopes around the world. Hopefully, a year from now, we're going to have 6 of them on Skynet, 3 in Australia, 3 in the US. And I'm making deals where they get to use the scheduling system for their own uses, but they give us a certain fraction of the time, typically 10%, as low as 3.5% on the big ones like the 30 meter we're integrating in Australia, but as much as 50% on some of the smaller ones. And so I'm finding the time, making it freely available to the Skynet community and remote telescopes. So you may think problem solved, but it's not solved because the educators, you all, don't have experience with radio. You're outside of your comfort zone. So that's part of what the MWU curriculum is about. It's trying to get not just a generation of students who will become the next generation of educators, but the current generation of educators. It's a chicken and egg problem. So we attack it from both sides, and hopefully in a generation, radio astronomy is as common part of the observational astronomy curriculum as optical, and everyone's as comfortable doing it. That's kind of the dream. Anyway, tangent. Okay, so last time I took it slow because, well, you don't have familiarity with radio for those reasons, that hopefully in the future, those reasons disappear. So introduced you to radio and how we make the maps by moving our 1-pixel telescope around, and how we turn those maps into images and all the different contaminants and how to process it. And we ended up by pressing the button and making our images and putting them in Afterglow. Let me get rid of the monkey here. And I've loaded them up, and we'll go back and you'll select ones to analyze, maybe the same ones you processed, maybe not if you weren't here. If you weren't here, you probably do want to watch the previous video to learn all that introductory radio stuff. But anyway, these are the ones we're going to be using. We looked at the moon and a calibration source, and we looked at Jupiter and a calibration source. And let's actually, before I go through these, I mean, they mostly just look like Gaussian blurs. As we talked about, single dish radio telescopes are blurry. But before we go through these, let's come back to our list of observations. And I'm sorry, for whatever reason, your names all got erased. So if you were here 3 weeks ago and processed one of these, feel free to stick your name. We did the orange ones. So in this region over here, go ahead and stick, let me put the link in the chat. Stick your name there to decide which one you're going to process, or not process, but analyze. These have already been processed now. So go here and claim one to do the analysis on. Let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of you. 1, 2, 3, 4, 5, 8. Yeah, so everyone take one and someone double up. And we will need everyone to participate because everyone's measurements will be critical to get to the end result. We're going to learn how to, now that we've made the images, learn how to make them. Now we're going to learn how to photometer. You're going to learn aperture photometry. Normally they learn this in the optical. They're going to learn in the radio in the MWU curriculum. By the time they get to optical, they're doing batch photometry, which kind of hides a lot of the mechanics. And so we're going to learn photometry. We're going to learn calibration. Students hate calibration. One, is boring and they don't understand what it's about, but it's, of course, so important. If you don't calibrate stuff, it's all meaningless. So we're going to learn calibration, and we're going to learn temperature calculation. Now, our targets are the moon and Jupiter, if you recall. And with the moon, our scientific question, everyone get your names in there. No one skip out. I need one name on each orange one.
We are just doing the orange ones.
Yeah, just the orange ones. Yeah. So the question with the moon is the radio emission. Is it caused by reflected sunlight? In which case it should change with the phase of the moon. And we took two observations at different phases, so we'll be able to tell. Or if not, if it's not reflected sun radio light, sun radio waves, then it is thermal emission from the moon, which would be pretty constant. And we can measure it. With Jupiter, the question is it thermal emission or something else? And so we'll start by assuming it's thermal, calculate a temperature, and ask, is that reasonable? Okay, what do we have here? Okay, no one wants to do. Okay, we're loaded up on Jupiter. Kent, you want to take one of these moon ones, even though you processed something different, perhaps?
I can do that.
Okay, appreciate it. Go ahead and take maybe this one, and I'll do both of these. Okay. So I'm going to stick you down here, Kent. Okay, great. And okay, we have everything covered. So what we're going to do now is get that data into Afterglow. If you already have it in from before, great. If not, you just click on the link. And we've already processed it. Now, many people may have processed it. The ones that we did, the last one here at the top, go ahead and click on it. That's probably the one we did 3 weeks ago, because I don't think anyone's been doing this. And all the settings are pretty standard. If you're looking at Jupiter, it says faint target. Otherwise, the moon or the calibration sources, it should say bright target. And then you download it. They're tiny files. And then after you download it, go to Afterglow, open files, and upload it into your workspace. Now let's see, files, you got to go into your workspace and then upload. So get it into Afterglow and then open it. And I have an example of each opened here. We used the crab as a calibrator for, let me check, Jupiter. And got 2 observations of Jupiter and 2 calibration observations. You only really need 1, but my students work in teams of 4, and I wanted everyone to do something. 2 of Cygnus, that's the calibrator for the moon. This time, just because the moon was close to it in the sky, Jupiter was close to the crab, so that was the natural calibrator. Let's see, the Cygnus ones, they all look like Gaussian blurs. Jupiter will look different because it's so faint. So it's very noisy, but it's there. Here are the 2 Jupiter ones. And yeah, with the Jupiter one, someone point out there's another source here that's probably a distant galaxy, a supermassive black hole. And then 2 of the moon taken at different phases. Okay. Does everyone have their analysis image uploaded in Afterglow?
Sorry, I think I missed something. I downloaded the file. Where do I go on the workbench to upload it?
Yeah, so you go to Open Files, you go to Files, Workspace, and then there's an upload. You can upload it
Oh,
into
there it
your
is.
workspace.
Okay,
Yep.
thank you.
It's a tiny file, so it'll be, really quick. And once it's in there, you double click on it and it will open.
Just the SD fits file that we download.
Yes, yes, it should be. I think it's a FITS file. So so the SD FITS is the raw data coming back from Green Bank. We processed it into an image. So
Okay.
it starts as a map, and now we have an image. And so here's a list of everything that's been processed. The one at the top is probably the last one we did. I don't think any other students have been to these pages since we were messing with them. And so you click on it, and that will load that one in, and then you can download it here. In these images, we've already done all the corrections. Just to remind you, here, I'll take one of these. I'm looking at the moon here. If I go down to, there are multiple layers here. The first one is the processed, cleaned image. The second one is the path map how the telescope moved to collect the data. It's been corrected. There's a time shift correction. Some points have been removed due to potential RFI contamination. The others don't matter, and you can look at the last one, and that's raw. If we don't do background subtraction, we don't do alignment, the time shift correction, we don't do RFI removal. That's what the raw data look like. And then back to the top, cleaned up, processed. So that's the RC algorithm, the radio cartographer algorithm, which is really powerful. We talked about last time. Okay, everyone ready to go? Okay, we're going to do aperture photometry. Let me just go to the manual here. This is the Moon manual. The Jupiter manual is almost identical. And here's an example. Here I've changed if you're working with one of the bright sources and you want to see the airy rings, just go to display settings, and instead of linear, change to maybe square root. See them a little bit. Let me go up to one of the crab ones here. It's usually pretty apparent with the crab.
Yeah, it's really obvious in the crab.
Yeah, see it there? That's the airy ring, the diffraction ring, because it's a circular telescope. Anyway, back to the manual here. 3 circles. The inner one is the aperture photometry. You're probably familiar with it. The inner circle is the aperture. We're going to sum up everything in the aperture. But as you're summing it up, you're also summing up the background. And so you have to measure the background. What's the average background in a pixel? For that, you have these 2 other circles farther away. And we actually position the first circle to lie between the source and the first airy ring, and the annulus to be out past the first airy ring. So it doesn't contaminate the annulus. And we average everything out here, or take the median probably. So it's less sensitive to any stray flux that might be out in there. And that's the background level. We subtract it off of every pixel that we sum in the aperture and get a value, a brightness value. And it's in kind of arbitrary units. It's in noise source units. I'll explain that in a minute. But let's actually do the measurement, or I'll remind you about the noise source we talked about last time. So we have to change our photometry settings for the radio. So go up here to settings, the gear at the top. Go over to photometry. And under aperture photometry, if I press this button, these are the default settings for optical. I need to add a button here for default settings for radio, but until then, we'll just type them in. It's these 4 boxes. Centering and aperture, we'll make those each 28 pixels. So the aperture will be of radius 28 pixels. That puts you right between the source and the first airy ring. The centering radius just means as long as you click within 28 pixels of the center, it will centroid. Then for the annulus, we want 50 for the inner and 70 for the outer. So 28, 28, 50, 70. And at some point, we'll add a button to make that a little bit easier. Everyone got that? Okay. So back to the workbench. And then if you go to the photometry tab, and normally I like to actually go to the sources tab first and make sure include sources from other files is off. Else, if you're doing many of these, and you're normally doing, today we're all going to do one, so it doesn't matter. But if you're doing many of those, the centroids don't pile up. Anyway, I turn include sources from other files off. I go to photometry and click on the center of your source within 28 pixels. See it's centroided. Give me an aperture. Give me an annulus. You'll all get that. Nice and easy. And here's the flux. And you want to write that down? I'll write, but let's see. Which ones am I doing? I'm doing the second moon. (15.369.614), and its calibrator. What was its calibrator? It was Cygnus. So I'm doing the second Cygnus. Oops, I want this one. Nope, the second Cygnus. Here we go. Now I'll get its value. 28595.786. Yeah, that's right. Okay. Okay, you all got one value, but write it down. Now, note the error bar is underestimated. This is using the optical aperture photometry routine, which assumes all the pixels in the image are independent of each other, which is the case in an optical camera. Each pixel is independent. Remember, this is not a real image, it's reconstructed. We collected data along only those points, and then through the RC algorithm, filled everything else in. So the pixels are indeed correlated, which means the photometry error bar is actually greater than what you see. We have an algorithm for it, but it's complicated and we haven't implemented it yet. The error bar, we're not doing that level of analysis, so you don't need the error bar. Okay, so we have a photometry measurement. And if we all go to this page, I'll put it in the chat. Here we go. Now we have two tabs, Moon and Jupiter. So if you're doing the first Moon one, what you just measured goes here. If you're doing the first calibration source, it goes here. I'm doing the second Moon. So I got 15,369. I mean, the decimal doesn't really matter. Go ahead and enter those numbers. Jupiter, you enter it on the next page over here. Second calibration source, 28595. We'll get the times in just a second, but I'll let everyone get their measurements in here. It is set to share, right? You all have access? No? Let me check. Oh, you don't. My bad. Yeah, I normally have this not shareable because I don't want people screwing this up. I make them make a copy of it. But today we'll all use this. Then I'll erase your stuff. Yeah, if you have like 100 students and you tell them to go,
Dan,
yeah, go ahead.
can you go back and tell me where you got those numbers?
Yes, they are. When you click on the source, it's right here under flux.
Okay.
Not magnitude, but here, flux. So it's measure the brightness in kind of an arbitrary unit. But I'll wait till you get your numbers in there. I did change it, right? You all have access now? Okay, there we go. Numbers coming in. If anything doesn't appear, I have them all open in my copy of Afterglow. You saw how easy it is, so I can grab numbers, fill them in. Yep, Jupiter's faint. Very good.
And the calibration source
Yeah,
for
so
the moon?
for the moon, it was right here. You see these pairs? The pair, whatever.
Okay.
So the Cygnus A. I did these ones. So this is you, Brad, right? You're doing the calibration source for the first one.
I'm trying to. I'm having the something got screwed up when I was part of the way through this. And I'm not getting the file to load up in Afterglow
Okay.
anymore. It just says tables are not yet supported when I try to upload the fits.
Hmm.
Also, it couldn't see the file
Oh,
when it
did you
was in
upload
my.
the SD fits or
Yeah,
did
that's
you?
what you get when you do the SD fit. Yeah.
Yeah, so you don't
Oh, what
want
did I?
this. You want to come down here, click on the most recent
Okay,
processed
that's what I
image,
did.
and then you go back down again, and there's a
Okay.
download button. Now, this interface here is a hack. We hacked it into Skynet 1. It's not the most pretty or easy to use interface. The goal was to not even integrate this until Skynet 2, but Skynet 2 has been delayed over and over, so we threw this in. Yeah.
See if that does the trick then.
It's a tiny file, so I bet it uploads real quick. Let me see how else we're doing. So missing that calibration. And on Jupiter, I'm holding your feet to the fire, everyone. Astro WE. Is this you, Christopher? You got the crab, a boss,
Yeah.
Ian.
Yeah. So should I be in calibration two, source two for Jupiter? Is that
Yes. Yep.
okay? My bad. My bad.
Christopher, your calibration 1 for Jupiter. David's Jupiter 1, he got his in a boss. You're
Oh,
Jupiter 1. Let me
I think I
see.
need to refresh because it looks like it's
Or Jupiter 2, I meant.
I'm sorry, my Jupiter one or Jupiter two?
Yeah, you are, check. You're calibration 2 for Jupiter 2. Yeah.
Okay, I'm sorry.
No, that's okay.
My bad. And I had to refresh because it hadn't picked up my
See how we're doing it. Anyone else need help?
Okay, that did get me to load the thing in. I kind of missed some of the steps after that, so
Okay,
I'm
so here we
a little
go.
behind.
Go to settings, photometry, and change it to 28, 28, 50, and 70. Here, 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 here.
Here. Okay.
Then when you do it, go back to the workbench, to photometry, which is the light bulb, and just click on the middle of the source, and you will have aperture photometered your source.
Excellent. Okay, there we
And the
go.
flux comes up over here.
Okay. So
Anyone else need some help?
Dan, can you show it to me again? Sorry,
That's
I
okay.
didn't catch it. Thank you.
I'm being mean today. I'm making everyone actually do it. So let's see. You're
I
this one.
uploaded, yeah, I uploaded that one on the
Okay,
Afterglow and
great. Good.
Afterglow.
So you have it uploaded. What was it? Jupiter 1, I think.
Yeah, I guess so.
Yeah, Jupiter 2. Jupiter 2.
Two. Yeah, yeah,
So that's this one right here.
yeah. I see that. Yeah,
It looks like that. Okay.
yeah, yeah.
Then for settings, photometry, 28, 28, 50, and 70. That will change it from optical photometry to radio. Those are setting the aperture sizes, basically.
Thank you.
Okay. And then you go back here to the light bulb and click on your source. And you should get something like that. And once you get it, enter it into the spreadsheet. Good. So we got all the moon stuff in there. The boss is doing this one. And who's doing Jupiter CalSource 1? Christopher, how's it going?
I guess I got lost. I've got two. I'm trying to figure out which observation. So I have one that's called crab, and I have one that I guess I did one from a couple of weeks ago, Jupiter crab.
Yeah, you're doing the crab here that goes with the first Jupiter. So it's this one right here.
Yep.
You click on it. Slide. Let's see. This one's only been analyzed once. So you click on it, and then you can download it.
Okay. So that's what I did.
Okay, and then you
Uploading it to.
Afterglow. Yeah.
Yep. On my tab. Okay.
Let's see, that's the first one. So it should look like that. And then for photometry settings, you go up to settings, photometry, 28, 28, 50, and 70.
Yeah. I'm sorry, Dan. I just
No, that's okay.
go on without me.
Okay. I'll grab your number for you there. So what was it again? It was the first calibration source. It's this one.
I'm on it now. Okay.
So
So
14,
Yep.
672. I'll just copy this and I'll dump it in the spreadsheet. We got it here. And we're missing a Jupiter. That was the Jupiter 2. And I'll grab that one right now. Now, what was it? Yeah, Jupiter 2. Okay. Okay, we got numbers in for everything now. Jupiter twice calibrated, the moon twice. Okay, here we go. 18 minutes. We're going to do this. Okay, now these are in noise source units. What's that number? What's the unit? So you may remember the way this works. It's kind of hard to see. Well, I'll go here. When we collect the data, we always turn on the noise maker at the beginning and the end of every map. I'll zoom in so you can see it here. So up in the receiver, there's just a little radio noise maker. We turn it on at the beginning and we measure the height of this. Then all the data is divided by that height. So the unit is that radio noise maker. It's unique to the telescope. But voltages, they drift and they scale. They stretch with time. So this takes that out because if the system's being more sensitive, the noisemaker, it has to go through the same system. So everything's been calibrated in terms of the height of the noisemaker. We now need to get that into Jansky's. Okay. So going back to the spreadsheet, it's all spelled out for the students with color-coded boxes. It should be very doable. Here we have the moon's flux density in noise source units. To get it in calibration units, well, the moon flux density in calibration units is its flux density in noise source units divided by the cal source flux density in noise source units. Basically, how many times the calibration source is your source. So let's see, I'm doing second Jupiter, so I'll show you I'll just use the equation. It's equal to my Jupiter measurement divided by my calibration source measurement. And you all can do that in your boxes. So one of you go in here and do it for these. It's just how bright was the moon divided by how bright was your cal source. It looks to be that the moon is about half the brightness of the calibration source. So feel free to, any of the moon or moon calibration source people, go ahead in here and add the equation like we did here. What just equal to the brightness of the moon divided by the brightness of the cal source. So this says the moon is 55% the brightness of the cal source, which was Cygnus. Good. Someone got this one here too, using the autofill. Great. Okay. Now we know the fractional brightness, the brightness of our target compared to the calibration source. How bright is the calibration source? So those of you who did calibration sources, that's given on this interface. You can click on it, radio calibration. Pick your source. So with Jupiter, it was the crab, which is Taurus A. And to fill in the frequency range that you observed, the date that you observed, you can just upload the same FITS file. Here's the second calibration source. And I uploaded it and it told me 846.1. But you go ahead and upload. Taurus sun does fade a little bit with time, but not over the course of a day. So you'll get the same thing. And someone should do it with the crab. No, this is the crab. Someone should do it with Cygnus for the moon. So 846, this is in Jansky's, 846.1. That goes here. So whoever did the second calibration source for the moon, you should go ahead and load your file in there. You'll probably get the exact same number of Janskys. Oops, that's the moon. My bad. 846 over here. Great. Y'all follow? I have all the images here so I can help, I can show. Let's see. If I upload the other Taurus, first crab is here, 846.2. Okay, it's fading by 1/10 of a Jansky every 4 days, apparently. 846.2 was the top one here. I'll go over to the moon. Good. Someone got this one in. The first calibration source for the moon got 1697. The second calibration source for the moon, that was the second Cygnus. $1592.3. It should be the same. I wonder why that's different. 1592.3. So I wonder how you got 1697. Who did this one?
I did. Hint.
Oh, okay. Let's see. So do you have these same numbers here? Cygnus never changes. So as long as you have the same numbers, you may have a different date. But upload the first Cygnus. Yeah, I got 1592.3.
Yeah, I got the starting frequency, stop frequency was the same. The date I had was 1:30.
Oh, are you set to Cygnus or Cass?
Oh, Cass.
Yeah, change it to
Okay.
Cygnus. Got the same?
Yes.
Okay, good. So I'll change you here, 1592.3. Okay, so what we did is we measured the moon is what fraction of our calibration source. We looked up the brightness of our calibration source in Janskys. That's why it's a calibration source. It's a source of known Janskys. And so now you can calculate. I'll do it on my Jupiter one here. Oh, I already got to it here. The Jupiter flux. It's just the multiplication of those two. So if you want Jupiter's flux in Janskys, it's equal to the moon's flux in cal units times the cal source in Janskys. So go ahead and multiply these two, and you have a flux for the moon. So we've now photometered our source and calibrated it. The moon's coming in at 855 Janskys on the second occasion. We'll see what it is on the first occasion in a second. And Jupiter came in around 3 or 4 Janskys. I'll slide the logic up here and just help you out. Okay, 878 on the first occasion. Okay, Now, so it looks like the moon's brightness is changing, but is that due to change in phase or change in distance? The moon's orbit is somewhat eccentric. So sometimes it's closer, sometimes it's farther. That's what we're going to figure out next. So in both of these, it's propagated to flux. We forgot to put in the dates. So let's get that date information for the moon observations. And that is on that Green Bank page. Like I'll grab the first one here. You know, I'm totally sorry. I thought I was doing Jupiter. I was doing the moon. Okay, so I'll grab the second one here. I somehow got confused as to what I was doing. So the moon was observed on 2:05 at 1826. So I'm going to put that in the spreadsheet. I'm doing the second moon. 2:05 at 1826. Go ahead and get the date and time in here. It's good to do it with all of them, frankly, just to confirm your calibration source was taken close in time. But these were. We have the same stuff over here on the Jupiter page. It's mostly just to confirm that these things were taken, that the calibration source was taken close in time. But we won't insist everyone do that right now because we're getting low on time. But we do need it for the two moon observations. There we go. Great. So one was taken on the 30th, one was taken on the 5th. So we're going to look up the moon phase and see if this changing flux is due to phase or maybe it's due to distance. So to get the phase, we have a nice little moon calendar here. And you can load it up and go back to that date. I think one was, what, February 5th, and one was January 30th. Don't know why it's not loading. Never had a problem with this thing loading. Now, of course, we do. Is it loading for you all? There's a little but. Oh, shit.
He'll rejoin.
Okay. And my internet kicked me out. So, all right. So, I think we left off was for the moon people, we're looking up the moon phase on these two dates.
Yeah, the 5th is the first quarter moon.
Okay.
It's 54%.
Yeah, there's a little button at the bottom on this calendar called illumination. You click that. And so we got 50% on the 5th.
The 30th is 2%.
Okay, so huge difference in phase. Go ahead and enter those phases into the two, and this one was what, 50? Okay,
Did you say 54, maybe?
54. Maybe someone looked it up
54.
precisely using the time as well.
Yeah.
So, is the moon's brightness due to reflected sunlight?
No.
No, because we went from no reflected sunlight to 50% reflected, yet the brightness of the moon actually went down a little bit. So it's not reflected sunlight. And so this variation is probably due to distance. And we're going to look up the distance now because that's going to be required to calculate the temperature. We'll probably go about 5 minutes over today. So distance, get the distance, we're going to load up Stellarium. And actually, you do need the time information for Jupiter, so you know what to put into Stellarium. Good, you got those in there. Great. So we have dates and times, the Jupiter observations. Okay, and so Stellarium. load up Stellarium. We're going to go to the location window and put it in universal time. So UTC 0. Search on your target. I was doing Jupiter, but I'm doing the second moon. F11 to shrink it. And we then enter that time. So I'm doing the second moon, I guess. So February 5th, 1826. Then you're looking for the quantity distance, not distance from sun, but just distance. That's distance from us in kilometers. Now, if you're doing Jupiter, it's in megakilometers. So you gotta, whatever the number is, e to the 6. So look up those distances and stick them in the chart here. We're going to need them in just a second. Second moon was 369734. And let's see. In the case of the second one, it was a little bit farther, so it's not surprising that the moon's a little bit fainter. With Jupiter here, go ahead and get your distances in. I'll help. I'll search on Jupiter and change the date. $17.20. So the distance to Jupiter on the second one, I'm getting 717.7 e to the 6. And the first one, 124. It's on my other screen. I'm just typing in that, and it's 119. Oh, you got it. Great. Okay. Super. Now, we're going to calculate the temperature. With the moon, we establish it's not reflected sunlight. So this is thermal emission from the moon. We're going to calculate its temperature. And with Jupiter, we're trying to figure out if it's a thermal source. And so we'll calculate its temperature and see if it's reasonable. So I'll type in the equation here, but it's Rayleigh jeans. With the students, I go to the module guide and explain it a little bit. Now here's the thermal spectrum, and I'll skip over this right now because we're low on time. But the amount of emission you get, the radio is down here, so we're in this limiting regime, the Rayleigh jeans limit. So the brightness that you get depends upon the temperature of the source. It depends upon the surface area, so R squared. It depends upon how far away it is. 1 over distance squared depends upon the frequency. And if you solve for temperature, you get this equation here, which is in the guide. And all the constants you need are here, so it's real easy. You take your measured flux in Janskys, multiply that by the conversion to get into MKS. 1 Jansky is 10 to the minus 26. Following the equation, divide by 2, divide by Boltzmann's constant, multiply by the speed of light divided by the observation frequency, quantity squared, times the distance, which we just got from Stellarium, squared, divided by pi, divided by the radius of the object, squared. You all can just Control C and dump that into your temperature box on either page. But normally the students go through and they code in the equation. I think it'll need an equals. No, you need to drag. I think you just copied this box. I'll drag it for you. Nope, that didn't work.
You can copy value as well. Paste value.
I'm just having a problem here. Is that not copying? Why is it 0? Here, I'm going to delete this. No one touch it for a second. I don't get it. Equals this times this divided by 2 divided by that times speed of light divided by frequency squared times distance squared divided by pi divided by r squared. Okay. So see, even though we had different fluxes, once you compensate for the different distances, we got the same temperature. We got 210 degrees Kelvin. Let's see how the Jupiter people did. That didn't work. I don't know why the drag is not working. Oh, I know why it's not working. Because the constants, yeah. The constants are getting shifted. The students usually each code this in themselves, and that's why the copy paste isn't working, because the constants are in different boxes once you paste it. Let me do it real quick. Brightness of Jupiter times the conversion constant divided by 2 divided by Boltzmann times quantity C divided by frequency squared times distance squared divided by pi divided by radius squared. There we go. Okay. And so here we're getting something like 2000 Kelvin. Now, since we're on the Jupiter page, let's tackle that one first. 2000 Kelvin, is that a reasonable temperature for Jupiter? Jupiter's 5 times farther from Earth. Earth's 288 Kelvin. And so 5 times farther away, you expect it to be colder, right? And we're getting 2000. So is this thermal emission? No, it's not. So that's the conclusion they reach here. What is it? Again, I'll do this quickly since I'm over. Case of Jupiter, it's synchrotron emission. So this is the introduction to another continuum emission mechanism. There are 3 of them: thermal, synchrotron, bremsstrahlung. Synchrotron is caused by charges in magnetic fields. And Jupiter has a very strong magnetic field. The charges get in there, they're trapped, they cycle around the field lines, and you get a spectrum like this. It's tilted completely the different way than thermal. And so often in the radio, much of what we see out there in the universe is synchrotron. The biggest synchrotron emitter in the solar system is the sunspots of the sun. These are regions where strong magnetic fields pop out and back in. It's ionized gas that those charges are cycling through. So even though they're dark spots in the optical, they're super bright in the radio. This is a VLA picture. Now the surface here, that is thermal emission in the radio, but the sunspots, that's synchrotron. Jupiter's magnetic field is so strong. It's like 15 times stronger than any of the other planets. In fact, we first learned of it when Pioneer 10 went behind it beyond the orbit of Saturn. The solar wind pushes it all the way beyond Saturn, which is nuts. That's how we discovered it. And so charged particles from the solar wind get trapped in here and emit synchrotron radiation. Also, particles coming off of Io, volcanic moon, it's spitting up these charged particles. It orbits within the magnetosphere. So that's also a supply of particles. Both of those make Jupiter glow in the radio. Now,
Dan, I'm not seeing your screen.
oh shit. I'm so sorry. Since I was kicked out and came back, I guess I haven't been sharing the entire time. This is one of those meetings where nothing's gone right. Okay. Yeah. Oh, I hate that. Ever since I came back, I haven't been sharing my screen. Okay, so I was explaining synchrotron, electrons cycling through the field lines. It's brighter. And for many sources, since the synchrotron spectrum's tilted the other way, it's very bright in the radio. Here's the sun that I was talking about. The magnetic fields coming out of out of the sunspots. So you have these really bright synchrotron emission spots on the sun. And here the surface, the blue in this image, that's thermal emission from the sun. Here's how we discovered Jupiter's magnetic field when Pioneer 10 was orbiting out beyond Saturn, passed behind it, and detected the field pushed all the way out there by the solar wind. Here's a diagram. So solar wind particles, but also particles coming from volcanic Io, which is orbiting within the magnetic field. Okay. That's the Jupiter story. And then the moon story, the way it wraps up. Actually, you can come back here. They measure about 200. So it wasn't changing with the phase. And radio waves are penetrating, right? We can listen to the radio through the walls of our house. So the radio waves coming from the moon are coming from a few meters down. And just like on Earth, you've been in underground caverns before. The temperature's uniform there. It doesn't matter what time of day, what time of season. You go down just a little bit, the temperature's uniform. That's what we're measuring here on the moon because the radio waves penetrate to that depth. It's going a few meters down. It's about 200 degrees Kelvin on the surface of the moon. And there's a link here on the moon page where you can actually look at professional measurements that were taken early on. Here, I'll click on 1 gigahertz. We're looking at 1.4 gigahertz. So here's 1 gigahertz. Here's a simple model. They get about 220. We got about 210. You can click on other people's measurements. And the students can ask, how they do compared to the professionals who originally measured this. And, they measured in kind of between 200 and 250. You can also check at 2 gigahertz. They're measuring about, 220 or so. And so what we measured was perfectly, here it is, perfectly reasonable. Anyway, I feel like that was a sloppy presentation. I apologize. When I was coding in the temperature equation, I guess I wasn't sharing. And so that was probably very boring to watch. I thought you were all watching me as I coded it in. So yeah, it ended not like I wanted to, but you get the idea. Between these two modules, they're very similar, slight scientific difference at the end. They're learning the basics of how to do radio with a little scientific question for them to answer at the end. All right, that's it. Thanks for staying late. I apologize for the technical problems.
Dan, you got just a minute?
Yeah.
Okay.
Thanks, Dan.
Thank you, Dan.
Sure.
Thanks. See ya.
Sorry, got kind of